paperwork to show the lecture notes. Okay. So first, old business. This came up yesterday. So remember we got into cylindrical tube hydrophones. These are annular cylinders, right? Inner radius A, outer radius B, some length, script L. And I mentioned to you that our procedure is actually approximate here. We completely neglect any electrical stuff. We just use the acoustic pressure to find the stress, right? And then from the stress, we can get the electric field, and from that we can get the sensitivity. The textbook makes no mention, I looked at it last night, it makes no mention that this is an approximation. I think it is an approximation. And the reason, it's a simple way to see this, and I should have told you this yesterday, but I didn't realize it until later. You can consider a sequence here in time where you have some stress, you impose some stress, right? You don't have I have the updated one here. I thought that looked funny. A stress will cause an electric field, right? This is piezoelectric material, right? But then an electric field, so we're looking at this as a sequence. This is sometimes useful. We look at it as a sequence in time. We kind of split it up into steps, what's happening here in time. We impose a stress, it's going to cause an electric field. But then an electric field, it will cause a change in stress. There's an interplay. You know, there's a reciprocity there between electric field, the elasticity, and the electric field. So it just goes back and forth. Eventually it'll converge. You know, if you imagine actually calculating this. So if you did, and there are cases where you can actually calculate this to infinity. I saw one once many years ago. This is kind of like successive approximations. If the contributions get less and less, you can just truncate this process. That's really the best way of thinking about successive approximations. We have a stress. We dictated by the pressure. We calculate the resultant electric field, and we don't worry about the fact that you really have to do this all simultaneously. That's the standard way that things are solved for. So I think that there's an approximation. The textbook makes no mention of this. It just states the procedure. So I'm going to check. Didn't have a chance. I'm going to check. I think Sherman and Butler, this other textbook that I mentioned the first day, so in Sonar Transduction. I'll check that. And another issue will come up in this lecture later, where a fundamental issue that I just don't think the textbook's right. So I'll have to. I'm going to check there too. Well, we'll talk about that when we get to there. Okay, so we did the theory of elasticity, mentioned that this is the general stress in a cylinder, or just pure elasticity, right? And then we discuss, we'll see these today, you'll see graphs of these today, these three different cases for the acoustic exposure. A is just the outside surface. We're shielding the inside and the ends. B is the outside and the ends of the cylinder. And C is the outside and the ends, but the ends are now capped. You get more force there. Okay. So completely neglecting any piezoelectric action here, we found these formulas for the stress in terms of the exposure coefficients, alpha, beta, gamma. Remember, alpha equals 1 means you're fully exposing the inside radius, inside surface. 0 means you're shielding it. And you can have any number in between. And then betas for the outside and gammas for the in. So the next thing we discussed is now we're going to talk about polarization. We're going to bring the electrical side in here. So the first thing we'll do is radial polarization. So that just means, of course, that the polarization is this way. The inner and the outer surfaces are electroded, right? Here's the general for E and D as independent variables. D is 0 here. There's no free charge involved. Right? There's a hydrophone, so D should be 0. So the electric field in the 3, we're now using the 3 refers to the polarization direction. Okay? It's not the same as the Z direction. We keep Z being the axis of symmetry. So we get this electric field. Okay. Now, remember, these stresses have a radial dependence. So now, to find the voltage, which is the integral of the electric field, you have to actually integrate. We just can't multiply by the thickness because it's a variable. You have to integrate. So when you do that, I'm just going to give you the result here. We find the voltage. It's proportional. This is proportional to the pressure, the acoustic pressure. Therefore, this is proportional. Therefore, V is proportional. When you take the ratio of the voltage divided by the pressure, which is the sensitivity, the pressure cancels out. In other words, this is all linear, like we've seen many times before. And here's the sensitivity. Now, it's a pretty long expression, but let me remind you, this includes an incredible number of cases. You know, really an infinite number, but practical cases is probably finite. So here's the result in terms of the, these are piezoelectric strain. These are like the D's before, but they're little g's now because we switched to independent variables. And you can look these up, right? This gives you the coupling between the electrical and the elastical and the elastic. Rho here is the ratio of A divided by B. So in general, A is equal to or less than B. So rho is restricted to this interval. It's not the density. So we've specified, this is for, you have to understand, this is for a radially polarized cylinder, being used as a hydrophone. This is the sensitivity. And you can choose whatever you want for the inner and outer radiuses, okay? And the exposures, alpha, beta, and gamma. So there's a, it unifies a lot of different configurations. Not just exposure to the sound wave, but also, of course, the radii too. All right. Now, you'll notice here, where's the length of the cylinder in here? Where's the length of the cylinder? It's not in there. And it better not be in there. That's actually a check. Because, whoops. We don't have a picture of this? Okay. All right. Let me go back, way back here then. So now we're electroded on the inner and outer surfaces. Sound waves coming in, causing compressions and expansions. We're looking at the voltage across the two surfaces here, right? If we double the length, what's that gonna do? Well, whatever is happening here is just gonna be duplicated down here. Is the voltage gonna change? Absolutely not. Okay, so that's, if we had, we can make a strong statement about that, and that's about it, incidentally, about the length. The length had better not be in the formula, and it's not. So that's actually a check, all right? So let's go down here. Now, I don't, these are, you'll notice here that it's proportional to B, but you need to be careful because B is in the row too. So the sensitivity is proportional to B if you keep rho constant. So in other words, if you scale this thing up, let's say you double A and B, okay, just remember, if you do that, the rho staying the same, and the sensitivity will double. And I don't think that's obvious. I don't think it's It might be physically reasonable, but I don't know. I don't think so. I don't think it's obvious. We have an electric field that's varying here. Now, if you dig into it, eventually it would probably make sense, but it's not on the same level as L. L just can't be in here. But the fact that this is proportional to B for fixed rho, I don't think that's obvious. It might be physically reasonable. I'll think about that, but I don't know. And the rest of the exposure parameters here is a fairly complicated dependence. So this is a general formula. It works for, as I said, many cases. We can look at it in a special case, a special application. Let's consider the interior and in are shielded, so alpha is equal to 0, gamma is equal to 0, right? And beta is equal to 1. That means the outer surface is fully exposed to the sound. And now you can just do this in your head. You'll see this collapses, it simplifies down to this. Now, typically, and we've seen this, typically it's like the D's, the little d's. These have opposite signs. So there's competition in the sensitivity. Remember, this is going to be positive here, because rho is less than 1, equal to or less than 1. Well, yeah. What happens when rho is equal to 1? What does that mean? We have an infinitesimally thin transducer. It'll break. Okay, so you can't get too close to rho is equal to 1. And that's actually interesting. We'll talk more about what the formulas tell us here as we go on. But anyway, I just want to point out right now that this is going to be positive. These things typically have opposite signs. So you're getting this thing we've seen before, this competition, and that can hurt you. And in fact, it's dramatic in this case. So to see that, let's take a specific material here, Navy type 1, okay, which is often used for hydrophones. The ratio, we can look, I just got this from the book, G31 over, here's G31 and G33. They have opposite signs. The ratio, that's all that's, for this being 0, all that's important is the ratio, okay? So if you set this, if you try to set this, to see if it's possible to have a rho where this is equal to 0, you just set this equal to 0, right? Divide by G33, so we're dealing with the ratio, and solve for rho. And it turns out you can find a solution. It's this. So when A over B equals about 0.4 roughly, you're going to have you're going to have essentially no sensitivity. It's going to be 0. Now, the way this is exhibited graphically is a little bit differently. You might think, oh, well, we can pick up material and plot the sensitivity on the y-axis and rho on the x-axis. They don't do that, okay? There's a more physical quantity here. And it takes a little getting used to. I remember I had trouble with this, but it makes sense. It's the ratio of the wall thickness to the diameter, okay? So if this is a top view, here's our ceramic. It's going to be this is B minus A, divided by the diameter, which is 2B. So that's the quantity you want to get used to. That's what's using here, what's being used here. So in this case, for this particular value of the ratio of A to B, it's going to correspond to a certain ratio of the wall thickness to the outer diameter. It happens to be to 2 figures. It happens, here's our physical ratio here. It happens to be 0.30. Okay, so here, let's bring these up here. So here you'll see, here's this physical quantity, the wall thickness divided by the outer diameter, okay? So we're looking there, that can run from close to 0, right, up to 1/2. It's limited to 1/2. It's important to realize the limit here, because we can check these. We'll be doing some of this, checking these as limiting cases. What does a value of 0.5 correspond to here? You have to think about it, but what does this mean? physically, geometrically? Anybody? Is it too early in the morning?
Radius of the entire, the radius is equal to the thickness?
You're getting there. It's a solid cylinder. Yeah, it's a solid cylinder. Okay, right. So that's a limiting case here. All right, so let's go through this. First of all, so let me keep these up and I'll be looking at this, the text here, notes. So this is the sensitivity. Okay, so this only depends upon rho, the ratio. So we can take the sensitivity, and because it's proportional to B for fixed rho, we can divide by that. Remember we talked, for the solid plate, we talked about the natural thing is the sensitivity per unit thickness, a simple example of the rectangular plate. So we can do that here. It's going to be, we'll divide it by the diameter, 2B. And everyone, this was, Cold War type stuff, so they're using inches here, right? So this is the sensitivity for a 1 inch as a function of this dimensionless quantity here, the wall thickness divided by the outer diameter. This is the sensitivity for an inch diameter hydrophone. If you have a 2-inch diameter hydrophone, you double it. Okay, if it's a 1/2 inch, you take 1/2. All right, so that's a nice way to do that. Oh, this is strange.
To picovolts?
Yeah, this is, and I have no idea how this happened, but people fall into things. They start doing things, they meet at conferences and they start talking, and for some reason, I have no idea how this happened, they got into picovolts per micropascal. Somehow they fell into that and it caught on, okay? And you can easily show that picovolts per micropascal is the same as microvolts per pascal. And this seems so much more reasonable. And, there's probably a reason why this happened. These aren't stupid people, right? And they're working on this stuff really hard, okay? So there's probably a reason for that. I don't really care what it is. I don't think we want to look into it. But I think it's much more reasonable just to use these units. These units. Microvolts, there's nothing wrong with microvolts per pascal. That's weird. Okay, so that's what's on here. Oh, I notice here, this is logarithmic. The y-axis is logarithmic. So it's covering a lot of, there's a lot of scaling over a pretty big scale here. So A is the ends and the inside are shielded. All of these have shielded interiors, okay? All of these cases, A, B, and C. A has shielded ends, B has exposed ends, C has capped ends. And you'll see that you can't get away from the fact, oh, this is a mistake. The graphics artist who did this, because this was, before PCs, this should go all the way down to here. It can't go to, this actually goes to 0, but that would be infinitely far down because this is a logarithm. Okay, but this should have been drawn all the way down to there. That's Brian's fault. He should have told the graphics artist. Did I talk to you guys about this before? Okay. Yeah, somebody actually drew this. Forget it. Okay, but this is back in the days where you had graphics artists and they actually drew this, and he should have caught this. This is confusing. It should go all the way down as far as you can go on this graph, okay? Down to there. So those are the 0. That's the 0.3 that we were just talking about. And you can see that when you do bring the ends in, it shifts it, but it's still there. It doesn't go away in this case, okay? And it's the same for Navy Type 2. It's similar. You can see these two are pretty similar. Oh, and in the caption here is to remind you the A, B, and C, because it's the first time we've hit this. We're going to see it again in other graphs for other geometries. So let me see if I'm missing something here. Yeah, all these cusps are zeros. Yeah. Okay, so one of the reasons this is important is if you just threw together a hydrophone right? You say, oh, this looks nice. You might be in this region right here, right? Let's say if it's a type 1, well, it happens to be the same there. But let's say it's with shielded ends, okay? If you're in this region here, you almost certainly want to avoid that. And you wouldn't know, if you didn't know the theory, you would, you build this thing and you test it and you say, God, it doesn't have a lot of sensitivity, okay? So the problem is that there's this competition between the two, these piezoelectric strain things. So the basic idea here is you got this hydrophone responding like this to a sound wave, right? So when it's compressed, and you're looking at the voltage across here, when it's compressed, the compression causes one voltage causes a positive increase, but you're also azimuthally stretching it, right? It's not just compressing and expanding this way, it's also azimuthal. So when it compresses here. We have these things called blackboards. Okay, you can compress it here. It's compressing here. That's going to cause the voltage to go one way. But it's also compressing azimuthally, right? That causes the voltage to go the other direction. So they're competing. And it turns out they can be zero here. This is extremely important. This can save a lot of trouble. You want to stay away from that region. Unless you want a hydrophone just for detecting a blast wave, I guess. I mean, just to think like a physicist here. There could be some possible use for being in this, you don't want to be exactly here, but somewhere in this region. If you want it to have low sensitivity. But, if there's a blast wave that's sufficiently big, you may not be around to analyze what's going on. I don't know. Okay. Any questions about that? So we're going to see more of these graphs in a few minutes.
Would the wall thickness and outer diameter ratios get really small? Like, that's not considering like how physically limited the material is. Like, it might break.
Oh yeah. So that's going to naturally come up. You'll see as we go on today, as we go on here. But you're absolutely right. So, you would look at this. We might as well we can talk about it right here. It's a good point. You see, wow, look at this, and over here, we've got these sensitivities on the scale here, 1s, 2s, 5s. Up here it's 100. So you think, oh, wouldn't it be great to have a sensitive 100? Well, you see what the problem is, right? The wall's thickness is going to be small, so it can fracture. So this is just theory, right? The application's left up to you, the actual design. You're going to have trouble here. Okay, so this is interesting. Next is longitudinal polarization. Okay, so now we're going to electrode the ends, right? And it'll be, of course, polarized in that direction too. So it's along the z-axis. Now, let me remind you what we just did for the radial case. We got d is equal to 0, and we got the electric field from here. Okay, and we had to integrate. All right. Now, if we try to do the same thing here, a problem comes up. So I want you to imagine, well, maybe I better do this. Okay, so now we're electroded here, polarized in this direction. Say, okay, d is equal to 0. We got to integrate this. So to find the voltage, let's say we integrate, from here to here. There's a big problem. The electric field, the stress depends upon the radius. Remember those 1/r²? So that means if we do that integral and then we do some integral here, we're not going to get the same value. We're not going to get the same voltage. These are equal potentials. We got to get the same voltage. They're at the same potential. They're conductors. So what's the problem? We've actually encountered something very similar to this before. I don't know if you remember. It was a length type expander bar where there were standing waves in there. You guys remember that? So it's similar. There's only one way out of this. You've got to get, the voltage has to be the same. The integral of the electric field has to be the same for all these paths here. There's only one way out. What is it?
Battery to it or something?
You're getting there. Even though, even though there's no free charge flowing here, there could be a free charge density. The total free charge has to be 0. But there can be a charge density. So what has to happen is, because there's free charge, it's total charge is 0, net charge is 0. The charge will migrate. There'll be a surface charge density. That's the only way out. So that means that we do have a D field now. We have to find the D field. Okay, so it was nice for a while dealing with hydrophones. We just set D is equal to 0. But now in this case, we've got to deal with it. Okay, now I've got to be careful because there's problems with the textbook, I think. So let me make sure we've got all this before we get into the next. Okay, all right, so we're here right now. Now, I invite you to look at the textbook. It's inconsistent here, and I don't know what the problem is. I'm going to give you my interpretation, okay? And again, I'm going to check this. I'm going to look in Sherman and Butler. I have Sherman and Butler. I have other older transducer books. I think I'm going to look in them too to try to resolve this. So this is my take on what's in the book, okay? The book is inconsistent. For example, it's treating this is the charge on the electrode. They're just treating this as the free charge. This should be 0. Okay? So I've reinterpreted this here. I've reinterpreted to what I think it's supposed to mean. All right? See, the textbook is also, oh yeah. The textbook uses this to find D, but it neglects E. Without any comment. It refers to this equation, and then to calculate D, it zeroes this out. So I'm interpreting this, and again, I don't know if this is right, is that this is negligible compared to that. It sounds like what we were talking about before, remember? When we find the stress, we find the electric field directly from the stress, where the stress is just found from elasticity, completely neglecting electrical effects. It sounds like that's what may be going on here. And I have to admit, this was somewhat of a concern in the past. I didn't get as deep. I got nowhere as deeply into it as I am right now. Okay, but I just kind of let it slide. Well, I think it's now time for me to try to figure this out. So I'll be working on this, and I'll edit the notes, and hopefully we'll resolve it. But I think there's a fundamental problem going on here. I don't know if I'll be able to resolve it. I'll do the best I can, but at least I'll be writing in the fact that this is my interpretation, so that you'll be aware that it could be wrong, okay? It's the least I can do, all right? Okay, so the idea here is we find D, okay, and then what can be done here, we can use the capacitance. Q is equal to CV, right? So often in the past when we found D, that gave us the free charge. That was, when dealing with projectors, that was a useful, you may remember, that was a useful quantity for us. So here it seems to be different. I don't think there should be any net free charge. But we can find this Q, and then from the capacitance relationship, because we essentially have a parallel capacitor here, right? Now we're this is a, do you guys, oh, here it is. This is for a parallel plate capacitor. The fact that it's curved shouldn't make any difference as long as it's, sufficiently small compared to the curvature. But the, whoops, we're going this way. Okay. Yeah, you can open this up. There's a little bit of a problem here. The field will, normally you look at this and you'd say the field's going to fringe. But again, because the epsilon here is typically in the thousands, that'll help trap those lines. So it's probably not a bad approximation. But if you make it too long, you're going to get a reduction in sensitivity. Okay, so anyway, this is a standard assumption, parallel plate capacitor. So we know what that is. We can calculate that. And if we find this Q from this D, it's the usual thing like Gauss's law that we saw before, we can find V. So that's what this is just a reminder. So here's the result. The textbook has the details of this, okay? But again, it seems to be inconsistent, at least to me. Here's the result for the open circuit sensitivity of annular cylindrical hydrophone, where it's electroded on the ends and polarized in the Z direction. Now, it's proportional to L. Does that make sense? It's got to be. If I double the length here, and again, neglecting diffringing, what's going to happen to if I double the length here, in other words, I take this and I just duplicate it down here, what am I going to find when I integrate the electric field over the distance? It's going to be twice. It has to be. So this has got to be true. So that's nice. We will then talk about a sensitivity per unit length of the cylinder. Bring that over here. It's a natural way to handle it. And well, I don't make any other comments here. We can look at various ratios rho, but I do that later. I think that's going to be later. Let's hold off. Okay, so we can get a physical feel for this. Kind of check it and see if it makes sense by looking at various limiting cases of rho here. And again, remember, this is general. The acoustic exposure is very general here. About as general as would be practical, I think. It's got alpha, beta, and gamma. Okay, so as an example, as an example of the application of this, let's take the simplest case, reasonable case here, alpha and gamma being 0 and beta equals 1. So we're just exposing the outer cylindrical wall, right? So when you do that, gamma is equal to 0, we just get, and alpha is equal to 0. You can see that it reduces to this very simple expression here. Now this, I hope I interpret this. Okay, so, so you'll notice, one of the first things you notice here is what happened to G33? It's gone. Well, so my reasoning here, I'm starting to wonder about that. Excuse me. Right. Remember now, there's no stress in the longitudinal direction. By the way, that's the 3 direction now. Sorry, because it's polarized in that direction. So this is the 3 direction. We're back to Z and 3, meaning the same thing. There's no stress in that direction. So I think that's why it's dropped out. Another thing you notice here is what happens when rho approaches 1. That's the thin wall limit, right? You'll see this is one of anybody dealing with transducers, they're going to say, first thing you're going to notice here actually is, so if we want high sensitivity, we just have to make rho near 1. Okay, we just talked about that, didn't we? It came later in the notes, but Stephen asked about it. It's going to be very thin-walled, so you're going to be limited there because the thing will fracture. And it could be hard just making it. You know, it's not necessarily fracturing in operation. It's just getting it making it. It can be hard to do that. Ceramics are tough to deal with. They like to fracture. That's why you don't want to drop them, right? And I'm sure that they're hard to machine. And this is something I don't know anything about, but you can cast them, right, in a mold. And we'll talk a little bit about that shortly when we get to the spherical case. But I think you can also machine them. But anybody know anything about this? So to be honest with you, when Brian taught this course, right, in the 80s and maybe into the 90s, probably into the 90s. Yeah, because once you come up with a book, you want to use it. You invest so much effort into it. So 80s and 90s, maybe 70s, I don't know. And then carrying on with Hoffler, the guy, he was followed by Hoffler, another transducer expert that I mentioned before. They did a field trip every time this course was taught. They went down to Santa Barbara. So there's 2 places where piezo ceramics are manufactured for sonar. There's one place on the East Coast somewhere, I don't care. In California, we don't care about the East Coast. I shouldn't say that, especially as it's being videotaped. It's just a joke, just a joke. The other place is Santa Barbara. I don't know how that happened, but I think it's maybe ITC is in Santa Barbara. I don't know. Remember so they would go down to Santa Barbara. And why did they do that? Well, you're seeing why. When me up here fumbling around saying, well, I think you can machine them. That's where you find out about all this stuff. You take a tour and you'll see. You'll actually, this guy will say, well, these are molds that we use, or here's this, these lathes with some kind of, special bits to cut. I don't know. I didn't go on a field trip. So anyway. So they took the whole day. It's a little bit of a distance. Okay, so the next thing, we've got our formula here. Remember, here's our general formula. Now let's do the ABC thing. Remember, that's different exposure values of alpha, beta, and gamma. So here it is. Let me bring these up. Let's focus on them. Okay, so now what you want to do now is, this is coming up next. This is a different geometry. Ignore this right now, okay? It's hard to ignore it. It's got these huge values here, but just try to ignore it, okay? And now this is our longitudinal case. And now it's interesting that you see in the B case where you have the ends exposed, now you can get this perfect, and this goes down to 0. This is nice. Or, this goes down to the lowest level on the axis. Again, this is logarithmic. So this is a 0, it's down at minus infinity. But at least it goes down to the bottom of the graph as it should. So the 0 now only occurs for when you have the ends, the B case, which is where you have, they're all outer wall is exposed. And this is just the ends. Excuse me. This is the ends. This is no ends. This is capped ends. Oh, that's nice. C for capped. That helps. Now you see, it looks like it's tending to go down here. So one way to interpret this is, it's tending to go to this complete, to get a 0, but it can't do it. One aspect overwhelms the other, and I think that's stated here what it is. It can't make it. So you're saved here, but here you got this problem again that you want to be aware of. Now there's a mistake in the book. This should be per inch length. Now we're talking about, right? It's going to scale with the length of the hydrophone. So this should not be diameter, it should be length, and that's stated in the notes. Okay, and again they got the screwy units here, we talked about that. So I'm going to go down below here, the notes below. So So the competing longitudinal and radial effects, there again we see this competition. It can only cancel for B. In A, there is no, I was wrong what I said just a few minutes ago. In A, there is no longitudinal effect, so you can't get cancellation. That's what we saw before, because there's no stress in that direction. Okay, so that's what happens in A. And in C, the way you can, now we have it there, but the compression this way dominates, causes the longitudinal motion to dominate the radial motion. You can't get the cancellation. Here's the domination one. Okay. Now there's something else here. You notice there's something else that again we're seeing this increased sensitivity. Oh, there's okay, somewhere I should come up with a physical explanation for why we're getting increased sensitivity when we go there. And it's going to come up, okay? But I need to put it earlier. So hold on, let me make a note here. I think it really should go back to the first one we did, the radial. Although there, you may recall, that tops out here. This is divergent. Okay, so this is even more serious. And we'll hit an explanation for this in a moment, I think, in the notes. But I want to look at the other side here. Why do those two things come together? This is actually easy. Here's
when it gets to 0.5, there is essentially a cylinder, right? So
it's solid, a solid cylinder.
Yeah.
So capped and exposed, they mean the same thing. So this is actually a check on the solution. The fact that B and C, they have to agree there because they become identical. They have to become identical.
I had a question about that though. So until that point though?
You mean like over here?
Yeah, C being capped, does that just mean that the electrode is covering the entire surface?
Yep, they got like a metal
disc.
Yeah, disc on there. Okay. Now, for the final cylinder case is tangential polarization. Okay? So, the textbook simply states the result. That means they probably refer to a JASA article for this. I don't know, I can't remember. But here's the result for the sensitivity. And it's, it includes an incredible number of cases, so we wouldn't expect it to be real simple. So it's the same idea. Here's the outer 2 pi b is the outer circumference here. And here's the number of segments in there, right? The number of segments. And maybe we should go to the graph here. And this is the only place I can find in the book where it's confirmed that you need to alternate the polarization, right? We've talked about this a number of times now, going back to projectors. Yeah, if you don't, you're going to get approximately zero. It has approximately zero sensitivity. Theoretically, it's zero sensitivity. And if you did this with a projector, as we first talked about this, alternating the polarization between the electrodes here, and you remember, like this is plus, they alternate. This is plus, minus, plus, minus. If you, if you did it for a projector, theoretically, it wouldn't work. It wouldn't get any sound. It wouldn't emit sound. You're canceling out. So you need to do that. This is the only confirmation on that. I mean, it's obvious, but again, as I've told you many times before, when I first went through this stuff, it's confusing. This is confusing stuff. It would help if it helps when authors are more explicit, and they get down towards your level. So this is the only place. It's that one little diagram. So I remember seeing that saying, oh, okay, so that's good. By then I figured it really had to be, but this is the confirmation. Now, the first thing you see here is that we got these huge numbers here. So this looks really good. But again, let me go ahead and remind you that you're going to have trouble down here because of the fracturing problem. The sensitivity is inversely proportional. Look at this. Divide sensitivity by N, capital N. Why is that? Physically, why is that? Think, this is like a capacitor here, right? And the voltage. If I double there's 4 segments here. That should be a capital N. Right? You see that there are 4 segments there? What if we doubled the number? What's going to happen to the voltage going from here to here? It's going to get halved. So that's why the sensitivity is inversely proportional to the number of segments. So you want to be careful when you see these large numbers here. Remember, you got to divide by N. Okay? Let's see. All right. That's Navy Type 1, incidentally. Well, that's probably in the caption. Now something happens. Now it's impossible, at least for these cases, at least for a Navy Type 1, for A, B, and C, you don't hit the 0 anymore. It's gone, okay? Something's noteworthy. Again, there's competition as you go out here. Now you'll notice here, these curves it looks like they're going to 0 here. Why is that? This is another one of those, if you just take a mathematical view here, you can say, well, I don't know why it's doing that, but it's actually, it's got to go. It's going to 0 because it has to go to 0. So I want you to imagine, remember, this corresponds to a solid cylinder. As you make these surfaces closer and closer, what happens to the voltage between the 2 plates? What happens when you go all the way down? You fill it all in. Just look what's going to happen to the electrodes. They short out. They touch. So I think this is going to 0 because these things are getting close to the voltage. Has got to go down because they're getting close. And then the limit they touch, you got 0 voltage. So it's nice to to put forth an effort. This is very simple, but it makes you believe this stuff. If it didn't go to 0, then you'd start to say, oh, this author doesn't know what he or she's talking about, right? And so this can be useful. It just takes a little bit of effort, usually. Or sometimes it takes a little bit of effort. Yeah, okay. Okay, so we only have a couple minutes, but I think it's all it's going to take. The final case, believe it or not, people have done spherical shell hydrophones. Jay says we used to have one here, but it mysteriously disappeared coincidentally with one professor moving on to Penn State going acoustics. Okay, so they can. Why would you go to the trouble, right? Well, first of all, how do you make them? Well, they can make solid shells, and I think it has to be a mold somehow, right? They also make hemispheres. You can probably machine those, I think, and then cement them together. The common case is to pull them across in the radial direction. So there'll be electrode on the inner and outer spherical surface. You have to have a little hole there to put a wire in to make contact, right? Just a little hole. That reduces sensitivity a little bit, but typically it's very small, or a small hole. Why would you do it? Well, one reason is I think they'll treat the outer one as ground. The inner one is then electrically shielded. So I suspect you could lower the electrical noise by doing that because the outer one, you're electrically shielding the inner one. Okay, so that might be one reason why they do it. So here's yeah, so it's presumably a mold. I don't know how else you do it. Anybody?
do glass.
Pardon me?
Unless they do it like they do glass and blow it.
Yeah. I've never, I don't know if, it's a good idea though. Yeah. Huh. Okay. Now, the textbook just states the result. And again, it probably refers to an article where you could read the details about all this. But one thing that's amazing here, so thinking of this as a sphere now, I guess we can leave this. Okay, thinking of this as a sphere, with a little hole here, so you can have a wire lead come here and solder it on here. Okay, this is the standard case, but believe it or not, they've done other polarization, other geometries, tangential polarizations. So what does that mean? Well, the only I can think of is you've got latitudes here, and how do I do this? Longitudes. So they're going to segment it now. Where do you segment it? How do you segment this? Now in the notes it says that the polarization, could be this way. It could alternate, right? That's what I thought in the past. These are the electrodes, but there's a big problem. I finally realized what happens up here. They all touch. So I'm going to change this. I think what's happening here is that they're going this way. They're alternating this way. And these are the electrodes. I think it's got to be, because otherwise you're going to have this shorting problem between. So I think I'm wrong here. So I'll edit that. So here's the formula. I think there'll be a homework problem and maybe even a quiz. Here's the result, similar to the other results. Okay. And I've looked at, we're going to have to stop, but I looked at several, you can look at this if you're interested, there's several limiting cases here. Remember, rho going to 0 is a solid, you'll have to have a little, you can't go completely to 0, right? You'll have a little metal sphere in the bottom here for rho going to 0, okay? And that rho close to 0. You have to have an inner conductor here. So that corresponds to the rho equals 0 limit. The rho equals 1 is the thin shell, okay? And now G33 is not involved because those expansions and compressions are negligible for a thin shell. So those are the two limiting cases. And here's a graph. The book does not have a graph, so I graphed it. Here it is, logarithmic scale. And it's typical to a radial. It's typical to a cylindrical. Typical numbers here. Microvolts per Pascal, okay? All right. Okay, so we'll finish this chapter tomorrow. We'll talk about noise.